between the electrode material as well as the current collector. Okay, so I will try to walk you through some of these examples which highlight these points that I already discussed. Right? One of which is think about this. If I'm sure all of you are familiar with what is called as these carbon nanotubes. Right? These are good materials as a supercapacitor electrode, which has already been extensively explored. Now, so if I were able to grow these carbon nanotubes, right, directly onto a conducting substrate, okay, if I can grow carbon nanotubes directly onto a conducting substrate, and then I can use that grown CNT on the conducting substrate directly as an electrode. Advantage is that these carbon nanotubes are nicely fitting or touching, right, molecularly bound to the these conducting substrates, which means like my current collector and the resistance is very minimum. Okay, that's very good. Otherwise, if I take some carbon nanotube, make a paste, and apply it on an electrode, there whatever you think it is tightly packed, there could be gap between the two, and that will lead to some drop in the resistance. Right. So this is one easy way of looking at it, and of course you can do a lot of studies to understand its improved performance of the supercapacitor performance. Right. Other way of thinking it is like it's a little bit different deviation from what I told, but then think about it. Right. Any energy storage device that you're using, whether it is a battery or a capacitor, right, it also needs to be looked at from the application point of view. For example, if I make a battery or supercapacitor, right, which domain or which application domain are we going to use it? Is it going to power your mobile phone? Is it going to power your other portable devices like laptops? Or is it going to power large-scale applications like putting it in a electric vehicle or large-scale grid storage? Or is it going to be used for powering very, very tiny devices? Right? When I mean tiny devices, it could be like very, very small electronic chip which needs some power. Right? Okay. So depending on these, the architecture, the material architecture is going to be different. Even if you are using the same material, I will have to design my material in a different way. Right? So for instance, we talk about these that's where we talk about these microcapacitors. Microcapacitors means like very, very tiny capacitors of the order of micrometer. Okay. And if I have a microcapacitor, means like very tiny, which you cannot see through your eyes. Those kind of capacitors, if you were to build it, then I can easily say that these microcapacitors could be actually loaded onto something like a power on chip devices. It can be basically called as a power on chip device, because very tiny supercapacitor, I can actually put it onto a nano circuit or a micro circuit, right? Otherwise, what happens is like for these tiny devices, right, you will have to attach a big capacitor unit or big battery unit, then the entire device size is going to be moved, isn't it? In order to avoid that, we try to make these kind of micro or nano supercapacitors so that these devices will have onboard power sources. Correct? And that is one example here. How do I make a micro supercapacitor? For example, I can do it this way. Sorry. For example, for a supercapacitor, well, you need an anode, cathode, and a separator as an electrolyte, right? So if I think that if I can grow these components like anode and cathode onto a nanowire, right, by making a bisegmented or trisegmented units, then finally a single wire will act as a micro supercapacitor or even a nano supercapacitor. I hope it's clear, right? Very, very tiny devices, very, very exciting to even think about it. Okay.